Hey there everybody, limits and differential calculus. Day number 7. Topic for today is implicit differentiation. We're going to use this concept of implicit differentiation to find the derivatives of the inverse trig functions. Let's get started. Okay, so an implicit relation is a relation where neither of the variables is the subject of the equation. More plainly put, the dependent variable is not defined explicitly in terms of the independent variable. So let's look at some explicitly defined functions. Here, y is explicitly written in terms of x, right? Same here in part b. Y is equal to the natural log of x plus x squared. So y is isolated, and it would be then a function based on the fact that there would be only one output per input. Okay, examples of implicit relations, okay, for a number of reasons here. First of all, y is not written explicitly in terms of x. Now, if I had manipulated to write that y squared equals negative x plus 5, I would still have an issue with explicitly writing y in terms of x, as this 2 here, y squared, would yield two possible functions or outputs for x. So we wouldn't have a function, we'd have a relation. Likewise, in part D, you're going to see that I've got y in multiple terms here, which would make it extremely difficult to write y in terms of x. Okay, this would be another example of an implicit relationship or relation. Okay, part E, this is interesting. This could be written as a function. If I were to change this exponential function into logarithmic form, I could write y explicitly in terms of x in this fashion. Okay, and then the last example, the dependent variable v is written in terms of two dependent or independent variables r and h. Okay, so v is not written explicitly in terms of r, rather implicitly in terms of r and h. We're going to work through a number of these examples by finding the derivative of the dependent variable using this method called implicit differentiation. Let's go ahead and get started. Okay, this process of differentiating an implicit relation specifically uses the chain rule. There might be other rules going on depending on what the function looks like. However, to differentiate, for example, number 1, we've got 3 terms, x, y squared, and 5. If I were to take the derivative with respect to x of x, that would equal 1. Very simple, basic differentiation. Okay, now if I were to differentiate the second term with respect to x, I don't necessarily know y's relationship to x. So I'm going to differentiate y as if it were a function of x. For example, if I were to differentiate the expression x plus 2 squared, I would use the power rule, which would make this 2 times the quantity x plus 2 times the derivative of the inside, which would be 1. I'm going to use the same process here for taking the derivative of y squared. I use the power rule, 2 times y to the first power, okay, to the first power, times y prime, which is the derivative of y. So you can see the correlation here between the power rule taking place and then the derivative of the inner function taking place. Okay, and then of course the derivative with respect to x of 5 will equal 0. So to write this, the derivative of x was 1, the derivative of y squared was 2y times y prime, and the derivative of 5 was 0. It's asking us to then find y prime. I'm going to isolate y prime by subtracting 1 and dividing by 2y. So y prime equals negative 1 over 2y. Now I did all of that without knowing the relationship between y and x. Okay, that's the process of implicit differentiation. Let's do the same thing here in number 2. Okay, the derivative of x squared with respect to x is 2x. The derivative of sine of y squared, that's going to require multiple chain rules. Okay, so I'm going to get the cosine of y squared, outer function, times the derivative of the inner function. The derivative of the inner function will be 2y times y prime. Okay, and then of course the last term is going to require product rule and chain rule. So I'm going to get minus derivative of the first function. Let's say the first function is 9x. We will take the derivative of that, which will be 9, times the second function untouched. Okay. Minus the first function left untouched times the derivative of the second function. The derivative of y will be y prime. Okay, we've got quite a bit of algebra here to do. Okay, so I'm going to find the terms that do not contain a y prime in them. And I'm going to bring them over to the right side. So that'll be 9y minus a 2x. And then I'm going to factor out a y prime. So if I factor out a y prime, I've got 2y cosine of y squared minus a 9x. Okay, so y prime will equal 9y minus 2x over 2y cosine y squared minus 9x. There you have it. That is the derivative of y in terms of x and y. Okay, outstanding. Now number 3, we've seen this as well. This is on the previous slide. I'm going to do this in 2 ways. I'm going to use implicit differentiation, and then after that I'm going to use just your explicit, typical differentiation methods. Okay, derivative of x squared will be 2x. Derivative of e to the y will be e to the y times y prime. Therefore, y prime will equal 2x over e to the y. Now, earlier we said that y could be written as the natural log of x squared. Now, take note, this is y. Okay, so y prime would be 1 over x squared times the derivative of the inside, which would be 2x. So y prime would equal, we'd get a reduction, this would be 2 over x. Okay, now let's look back and see how these two are equivalent, seeing that, well, they don't look the same, right? All right, so we have identified e to the y as x squared and 2x. So y prime equals 2x over x squared. Well, when I reduce that, that would be 2 over x. And there you have it, okay? Those are equivalent statements. However, if you were to use implicit differentiation, you would leave your answer just like that. Okay, let's look at a few more examples. All right, in example 4, for f, I don't know about for f. How about for v? For v, find dv dt in terms of r, h, dr dt, and dh dt. Now notice, prior to this example, we are always differentiating with respect to x. In this case, we're throwing in a fourth variable. So I'm going to take the derivative of v with respect to t. The derivative of v with respect to t I would write as dv dt. Now, in the remaining portion of this problem, I'm going to consider 1/3 pi as a constant that I'm just going to carry out. Okay, and I'm going to take the derivative of r squared times h. Okay, so the derivative with respect to t of r squared times h is going to be 2r times dr dt, right, using the chain rule, times the second function left alone, which is h, plus the first function left alone times the derivative of the second function, which is dh dt. So that'll be 2r times dr dt times h plus r squared times dh dt. And there we have dv dt. So the change in volume with respect to time will be 2 pi over 3r dr dt times h plus pi over 3 r squared dh dt. Now let's talk a little bit about these variables. R is just the radius, and in this case that would be the radius of a cone. H is the height of the cone. Dr dt is the change in the radius with respect to time, or the rate of change of the radius with respect to time, and dh dt is the change in height with respect to time. And that's all equivalent to the change in the volume with respect to time. Okay, these skills seem kind of redundant. However, in our next lesson on related rates, we'll see how this applies. Let's look at the example below, number 5. Number 5 says, find dy dx for x cubed plus y cubed minus 9xy equals 0. Then the tangent line to the curve at the point 2, 4 in the form ax plus by plus c. Okay, so let's go ahead and let's differentiate our expression. So let's take x cubed plus y cubed minus 9xy. Okay, I'm going to take the derivative of all of these with respect to x. So the first term, relatively easy, power rule, nice. We use the power rule in the second portion. However, then we also use our y prime notation. Now this problem asks for dy dx, so I'm actually going to utilize that notation, dy dx. And then I'm going to subtract using the power rule, or excuse me, the product rule, 9 times the derivative of x times y, which is 1 times y, plus x times the derivative of y, which is dy dx. And the derivative of 0 is 0 on the other side. Let's clean this up. This will be 3x squared plus 3y squared dy dx minus 9y minus 9 times x times dy dx. Okay, all terms that don't contain a dy dx, I'm going to move, bring those over to the right side. So it'll be 9y minus 3x squared. Okay, and I'm going to factor a dy dx out of the remaining terms. That will be 3y squared minus 9x. Therefore, dy dx is equivalent to 9y minus 3x squared over 3y squared minus 9x. At this point, if I wanted to, I could simplify. I think I might keep my math a little simpler. I'm going to factor a 3 out of everything. So that would be 3y minus x squared over y squared minus 3x. Okay, now I'm being asked to find, let's see here, the tangent line. Well, the tangent line equation should have a slope. So I'm going to use this slope at the point 2, 4. Well, that would be 3 times 4, which is 12, minus 2 squared, which would be 4, over 4 squared, which is 16, minus 3 times 2, which is 6. So the slope of the tangent line at the point 2, 4 is going to be 8 over 10, so 4/5. So the tangent line equation is going to be y minus 4 equal to 4/5 x minus 2. There's your tangent line equation in the form, point slope form. Let's put it into the standard form. So I'm going to distribute 4/5. So that'll be 4/5 x minus 8/5. Let's bring everything over to that left side, setting the right side equal to 0. So that'll be negative 4/5 x plus y. And then I'm guessing that'll be a minus a 12/5. So I've identified A as negative 4/5, B is 1, and C is negative 12/5. There you have it, guys. That is a pretty typical implicit differentiation problem. Let's keep going. We got about 3 slides left here and see what we got. Okay, here's an example looking at ds dt. S is surface area of a cylinder. Find ds dt relating the rates of change of the variables of S. So the variables being R and H. So we looked at a problem similar to this a couple slides ago on the volume of a cone. Let's do the same thing here. So the derivative of S with respect to t is ds dt. Okay, the derivative of 2 pi r squared with respect to t will be 4 pi r times dr dt. The derivative of 2 pi rh will be we're going to use product rule here. So I'm going to actually put 2 pi out and take the derivative of r times h. So the derivative of the first would be dr dt times the second left untouched plus the first left untouched times the derivative of the second. Okay, that would be kind of the lazy person's way to finish this problem. So I'm going to clean it up just a tad, see if there's anything that I can simplify here. I don't think there will be much. 4 pi r dr dt plus 2 pi dr dt times h plus 2 pi r times dh dt. Not a whole lot I can do there, but that would be it. Okay, pretty simple there, using just a little bit of chain rule work and the product rule. Okay, let's look at our next example. Okay, so now that we're relatively comfortable with the chain rule and its use in implicit differentiation, I'm actually going to show you how we can use implicit differentiation to find the inverse trig derivatives. So first thing I'm going to do is write arcsine with a y instead of f of x. Okay, now I don't know what the derivative of arcsine is, so I can't take the derivative, right? Right now it's explicitly written y in terms of x. So the inverse of arcsine is sine. So I'm going to take the sine of both sides. That gives me sine of y equals x. And now I do know what the derivative of sine is, and so I can use implicit differentiation in order to take the derivative and work this out. Okay, so I'm going to take the derivative of sine of y. That will be cosine of y times y prime, and the derivative of x is 1. Therefore, y prime is equal to 1 over the cosine of y. Now, what the heck does that even mean? Well, let's look back at the original. Y equals arcsine of x. So let's look at the following. recall that if I take the arcsine of a ratio, I get an angle. So y is an angle, and x is a ratio. So y is an angle. The arcsine of x, so that means the sine of x the sine of y equals x. So opposite over hypotenuse, which using the Pythagorean theorem would give me an adjacent side of square root of 1 minus x squared. Okay, so y prime is equal to 1 over the cosine of y. Well, what is the cosine of y when we look at this diagram? The cosine of y is the square root of 1 minus x squared over 1. And therefore, since that's the cosine of y, the derivative, that's just awesome, of arcsine of x is 1 over the square root of 1 minus x squared. Okay, arc cosine of x, very similar. I'm actually going to use a different notation here just to show you that they're equivalent. That means that the cosine of y is equal to x. The derivative of cosine is negative sine of y. And then using the chain rule, I multiply by y prime. And the derivative of x is 1. So y prime should equal negative 1 over the sine of y. Okay, let's draw another diagram. Okay, if the cosine of y is x, then adjacent over hypotenuse is x over 1. That leaves this side as 1 minus square root of 1 minus x squared. And therefore, the sine of y is opposite of the angle over the hypotenuse, which gives us a very similar, yet not the same result. The derivative of arc cosine is negative 1 over the square root of 1 minus x squared. All right, let's look at tangent. Again, I'll use this alternate notation. Either is fine. So the tangent of y is equal to x. The derivative of tangent is secant squared. Using the chain rule in an implicit differentiation, I get secant squared y times y prime equals 1. So y prime is equal to 1 over secant squared of y. Let's draw a diagram. The tangent of y equals x over 1. That leaves the hypotenuse as square root of 1 plus x squared. The secant of y is hypotenuse over adjacent. Now if I square that, then the secant squared of y is equal to 1 plus x squared. So y prime is equal to 1 over the secant squared of y, which is 1 plus x squared. And there you have the derivative of arctangent of x. Outstanding. We got one more slide here. Let's see what we got. All right, awesome. Here we've got just the general derivative for an inverse function. Okay, so generally speaking, okay, I don't know what the function is, but generally speaking, if y equals f inverse of x, then f of y equals x. So I can differentiate this implicitly defined function by using the rules that we've done so far. I'm going to take the derivative of the outer function times the derivative of the inner function. And of course, the derivative of x is 1. So y prime will equal 1 over f prime of y. So the derivative of an inverse function will equal 1 over f prime of f inverse of x. So let's look at an application of how to use this. Now, once you have these memorized, it doesn't really matter. You can just use your inverse trig derivatives to execute whatever you're being told to do. But let's just say that an inverse function, inverse f of x, is arc sine of x. That means that f of x would be sine x, right? Okay, so let's look at what the derivative then, based on this formula that we've just put together, of arc sine of x would be. Well, I know it would be 1 over something, right? Now, what is that something? That something is the derivative of f. Well, what is the derivative of f? Well, f prime is cosine of x. So I would have the cosine of the inverse function. And that inverse function is arc sine of x. Now, what does this actually mean? Right? What is the cosine of the arc sine of x? Well, I can sketch myself a diagram like we just did in the previous problem, where the arc sine of x equals y. So opposite over hypotenuse, x over 1. That leaves our adjacent side, square root of 1 minus x squared. So the cosine, right, this is just an angle y. What's the cosine of y? Well, it's the square root of 1 minus x squared over 1. Therefore, this is equal to 1 over the square root of 1 minus x squared over 1. And there you have it, right? I can use this simple rule. It's very helpful outside of derivatives that we've already memorized. So there is your rule. I'm going to put that in green here for finding the derivative of an inverse. That's useful if it's just not a function that you've had to differentiate very often. Okay, guys, that is day number whatever this is. So you got questions, you shoot them to me. You want a workout plan, let me know. Have a good day. We'll see you in the next video.